So we were about to introduce an algorithm which checks the planarity of a given graph G and produces a planar embedding if the given graph is planar. So let's describe the algorithm. First, it's easy to see that as long as we can consider the two connected graph G, if we can check for given two connected graph G, if we check the planarity, or if we know how to embed these two connected graph, then it's enough for our purpose. Because if the graph is not too connected, we consider each block. And if we know that every block of this is planar, then the entire graph is planar. And if the entire graph is planar, then every block of this is planar. So once a graph is given, we just check the planarity of each block, then it suffices for us, for our purpose. Moreover, if we know how to embed each block, then we also know how to embed the entire graph. So we just, consider a two connected graph. So, and let's say, if we have only graph with only two vertices, then it's easy. So let's just assume that we have a two connected graph with at least three vertices. It's given as an input. And what we first do is we choose an arbitrary cycle and name it G0 of G. And what we do is we first, embed this G0 in the plane with two face boundaries consisting of its vertices. So we embed this G0. And now we iterate the following. So for given G0, Gi, which is already embedded, we find Gi plus 1 as follows. So this G0 or Gi is a plane graph which is already embedded. First, we determine all Gi fragments of G. Let's just assume that we have Gi, which roughly looks like, say, this. And if, there could be several fragments, looking this way and say this. And what we do is for each Gi fragment, say B, we determine all faces of Gi that contains all vertices of attachment of B, and we call this FP. meaning that for this fragment, its vertex of attachment are these three. And among the 1, 2, 3, 4, 5 faces, only this face contains all these three vertices. This outer face also contains these two, but it doesn't contain this third vertex. So for this B, the FB is exactly this face F. On the other hand, for this fragment, we know that if we say that this is F1 and this face is F2, then the vertex of attachment are these two vertices, which are contained either this face F1 or F2. So in that case, let's say this is B, then FB is F1 and F2. So there could be also a case that this could be much larger. For example, if we have, say, F1, F2, F3, F4, F5, and F6, and we have the fragment looking this way, then if this is B, FB consists of all these faces. Anyway, we can check this, and we define this F of B. And if this FB is empty for some B, then we end the algorithm and we return non-planar. Our conclusion is that this graph is non-planar. And end the algorithm. And if f of b is 1, so there exists one fragment which is attached to only one face. So for example, here, this fragment is attached to only here. For some p, then we select such p. And if f of b is bigger than 1 for all b, then we select any b. And since we don't know how, let's say, each fragment could be very complicated. We may not know how to embed all of them. So instead we choose a path P between two vertices of attachment of the selected B. And we embed this P across a face in this FB. And we call the resulting graph GI plus 1. Meaning that in here we have this, and we choose this, say, one path, this arbitrary path, and embed that. Then this is gone now, and this becomes this. Now this new black part is GI plus 1. And now this becomes a new fragment. But we have embedded more. So we'll call this new graph GI plus 1. And we update the list of face boundaries. Wait, why did I write 6 here? 4, 3, 4, yep. And 5, if this GI plus 1 is entire graph G, then we return planar. Otherwise, we increase I by 1 and return to step 1. So we repeat this. After that, again, you say choose now, say this edge. Then FP is either F1 or F2. So you choose, say, F1. Then, how do you do it? Is you embed this path here. Now, the remaining thing become this. And this remaining is the new fragment. So this is our algorithm. And then we want to prove that this algorithm indeed produces a planar embedding if the given graph is planar. So algorithm above produces a planar embedding. If G is planar. So we know that this G0 extends to a planar embedding. Of G if G is planar. So what I mean is that if G is planar, that means there is one way to embed it. And in that embedding, if we find the cycle G0, then it is embedded in some way. Let's say this is the cycle. And it is embedded in here. And it could be either embedded, say, 1, 2, 3, 4, 5. And if you just embed this G0 in arbitrary way, then it's either 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5 in clockwise or counterclockwise. But we know that this I cannot reflect. Anyway, so this can be, you can take a mirror image of this. So if G can be embedded this way, then you take the mirror image. That 1, 2, 3, 4, 5, and here is 1, 5, and 2, 4, 5. Then this is also on planar embedding. So if we embed this G0 in an arbitrary way, then this extends to here. So this always extend to one of these two. So we know that this embedding, arbitrary embedding of G0 always extends to the embedding of entire, planar embedding of entire graph G. So what we want to show is the following. That if the plane graph GI is extendable, extendable means that once you have an embedding of GI, and then you try to embed the rest of the graph in G, rest part of the graph in G, which, this is already fixed. We don't change it. And then remaining thing we embed in certain way, which coincides with the embedding of GI, so that the entire graph, entire embedding we get is a planar embedding. That means it's extendable to a planar embedding of G and the algorithm produces a plane graph GI plus 1 from GI. Then we want to show that this GI plus 1 is also extendable to a planar embedding of G. So since we know that G0 is extendable to a planar embedding of G, if G is planar, so if we prove this, then we can show that G1 is also extendable, and G2 is extendable, G3 is extendable, and we can say Gm is extendable when G is G. So that means G is planar. We get a planar embedding Gm, which is exactly G, which is already embedded on the plane. So this produces a planar embedding. And note that every GI fragment P has at least two vertices of attachment. As G is 2 connected. So let's consider two cases. There are two cases, right? In this algorithm, what we do is we embed this, we choose this B according to whether there exists some fragment with FB at least size 1 or exactly 1. Okay, so before doing this, let me recall again. Say, consider this simple example of K4. Give me a moment, not this. Yeah. Let's consider this simple example of graph. And if we do the above approach, let's say we embed this 1, 2, 3, 4 and this 1, 2, 3, 4. And now for this, this part, this is a fragment. And assume we have chosen to embed it here. And then for this fragment, now we assume that we choose to embed it here. Then for the last fragment that we want to embed, you cannot embed it here and you cannot embed it here. So if we choose, these 1, 2, 3 in this way, then even if this graph is planar, you might not be able to produce a planar embedding, right? So we want to show that the reason why we end up in here is that when you embed this, these two fragments, we made a wrong choice. There are two choices, right? This one can either go inside or outside, and this one can go either inside or outside. And we should have embedded both of them into the same part. So if we have embedded in this way, then it would have been fine. So when there are some B with more than one choice, we have to make a good choice, otherwise it would be a problematic. And we want to show that this rule. So what's the rule? If there is B with a choice exactly 1, then we always select this. That will guarantee us that this bad event doesn't happen. That's what we want to show. So first, if this one is 1, for some GI fragment B, then only one face of GI contains the path P in an extension of GI to a planogram. Embedding of G. So what's our assumption? We assume that the GI is extendable to a planar embedding of G. So that means for given G, GI already embedded, there is at least one way to embed it. Let's say embed the rest of them. Once you embedded the rest of them, so this is one fragment, so this is one fragment, then in this embedding, so this is B and this is F, and F of B is exactly F, means that in this extension, this is already here. That means if you choose this P that we want to embed, then that's already inside of here. So the algorithm puts P in this space to obtain GI plus 1. So in this case, GI plus 1 is extendable, because we already have this G head which extends GI to here. And even if we put this inside of here, then that coincides with how we put it here topologically. Topologically they are same, so there is way to extend the rest of them. So in this case, everything is fine. So problem can arise only when this available faces for each fragment is bigger than 1 for all B. And we select the wrong face, maybe all wrong face. To say receive the selected face path P. Now let's suppose that we embed P in face F. So that's what algorithm did. And GI extends to a planar embedding, say G hat of G. In this specific embedding, P is inside some other face, say F prime. So we have GI and we have this, say, fragment, and we embed this. Let's say we have F and F prime, and by our assumption there is a way to embed GI to G hat, which we don't know. We don't know how, but we know there exists one. And in this way, let's say this part is here. But here we actually decide to embed this path into here. So we know that if we have made a choice into F prime, then this could embed, but we made the wrong choice, F. Then what we want to show is that even in this case, there is another way of embedding rest of the graph in this way. So entire G can be embedded into this plane graph G prime, so that this fragment is actually in F instead of F prime. Then we prove that this GI plus 1 is also extendable to a planar embedding of G. So as long as this, each time we show that there exists one planar embedding of G, which this embedding is extending. But this planar embedding and then this planar embedding that we found doesn't have to be the same. Of course, the specific planar embedding of this is one of the possible ways of embedding GI. But at this point, there might be 10 ways of extending GI into planar embedding. And now there could be less than 10, 5 ways to extend here. But it doesn't matter. As long as there is at least one way, it is okay. And that's what we want to show. So now we want to modify this G hat into this G prime, which this path P is inside F. That will show that the G sub I plus 1 is extendable. So let C be the set of vertices in the boundary of both F and F prime. So in this case, C is these ball vertices. And this includes the vertices of attachment of B. And what we do is we draw G prime by switching between F and F prime. What we switch is all GI fragment that G hat places in F or F prime, and those whose vertices of attachment lie in C. So let's say, the situation could be more difficult, that these are actually vertices of C, but let's draw a bit simple way. So here we have F and F prime, and we have B here. And there could be, other way of embedding. There could be other fragment. And now what it says is that also there could be, say, let's not use the red color. So among these, so this is G prime. So this is how we embedded G prime. So this specific B is embedded in F prime. But now what we do is among all fragments, this blue and red one are embedded in F prime. And also whose vertices of attachment lies in F. Let's change this green thing into here to explain here. So C is this vertex, this vertex, this vertex. So this is C. And this has a vertex of attachment here, and this fragment has vertex of attachment here, and this has vertex of attachment here. So what we do is we take this and then we move here, and then we take this and we move here. All red, blue attachment we embed it here, we reflect, we move it here, and this green we move it here. That's what we do it here. While doing that, we keep this purple one and we keep this purple one because its vertices of attachment are not in C. Also, we keep this orange one in here. So that's what we do it here from this G head. This changes. Switch B and produces the desired embedding G prime unless some unswitched GI fragment say B hat conflicts with a switched fragment. So in this case, if we do that, if there was no this orange one, then it would be fine. It's again a planar embedding. But now, because of this F, if we move it here, then this would look like this. No, this. That would conflict with this orange fragment, so it becomes non-planar embedding. But if orange one was not there, then we can always move this to here, and this to here, and this to here, and then this to here. There will be no problem. I mean, let's say that there was one more vertex here and here. So, I mean, if that's why we need to move this, I mean, green one to the other side. If we just move this red one to here, then the red one and green one conflict with each other so that we don't get the planar embedding. Anyway, this yellow one is problematic, so we give the name of B hat to this yellow one. That's the one conflicts with one of the switched one of this red or blue. Since the switch is symmetric in F and F prime and changes only the interior, so we may assume that this B hat appears in, say, F in G hat, like here. I mean, there could be that this phenomena appears here, meaning that there could be, I mean, some things. Anyway, so we assume that this is here. If, I mean, it happens in either F or F prime with a different way of drawing it. Here, the drawing is, I mean, it's not possible to appear in here, but so we assume that this appears in F, in this G hat. And here, again, conflict means G hat has some B prime in F prime, which we are trying to move F such that P hat and P prime are adjacent in the conflict graph of F. So let's choose one of these three. Any one of these three in this case can be B prime, which conflicts with this P. So let A hat and A prime be the vertex sets where P hat and P prime attach to the boundary of F. So let's say this, again, red one is P prime. Then we say that A prime is these two vertices and B prime is these four vertices. Since P hat and P prime conflicts, then A hat and A prime have three common vertices or four vertices which say alternating vertices on the boundary of F. Since what do we know? We know A prime is lies in C, but A hat is does not lie in C. Because again, what we switch here are all the ones whose vertex of attachment lies in C. So B prime also has, these vertices of attachment which lies in C. But here we didn't move it to other, meaning that it has at least one vertex which is not in C. Because of this, we know that the first possibility implies the second. We have F, and then there are three vertices here, and then this has one outside. Then we can simply choose P1, P2, P3, P4, so that P1, P3 has a neighbor here, and P2, P4 has a neighbor here. So this is same as the latter possibility. So let X, U, Y, B be the vertices with X, Y in A prime, which lies in C, and U, V in A hat. So you have F, U, V, and X, Y. So we may assume that U is not in C. So this is not in C. So, we can assume that if there are no such, alteration, then, B hat and B prime do not, conflict. And, yeah, that means the if, this is not true, then we would have moved this P hat to the other, which would cause no problem. So we may assume that this one vertex is not in C. And since U is not in C, and Y is between U and V on this F, no other face contains both U and V. So meaning that these fragments are not yet embedded. Wait. No, sorry. So this entire thing is how it's embedded in G hat. Entire thing is embedded. So we have give me a moment. So this space is F in GI. So in GI, in the embedding of GI, we say that inside of this U and V, you have this F, and you can find the path between here. No, sorry. Let me. Give me a moment. U is between Y is between U and V on F. Okay. If there is another face F double prime containing both U and V, then what happens is that in this F double prime, so in this F, we can find the path between U and V. And in this F double prime, you can also find the path from U and V. So this gives us simple closed curve on the plane, which by Jordan curve theorem, which separate Y and X. So if you delete this F and F prime, that deletes, this simple closed curve as well. It separates the entire plane into two, one containing Y and one containing X. So there could not be any one face which contain X and Y together in this, GI. There are no face which contains XY, which is a contradiction. So then, because we already say that XY both lies in C. And this C, we know that this C lies in both F and F prime. So this is a contradiction. That means that no face contains both U and V except this F. However, then that's a contradiction, right? In our algorithm, what did we do? If there exists such B with only one possible choice, then we always select this. But what we have assumed here is that we chose B because for all possible choice, this FP is always bigger than 1. But here we have this B prime. No, not B prime, B hat. What is the B hat? B hat is a face inside F, which has X and Y, U and V as its vertices of attachment, and there are at most one face F which contains both vertices. So there are at most one face which contains all vertices of attachment of this B hat. So this fails to have its vertices of attachment contained in at least two faces contradicting the hypothesis that this is always bigger than 1. This is bigger than 1 for every fragment. That was our assumption. So this proves the theorem. So this shows that before we have this, say, this embedding, once we have embedding of this cycle, and then we decide to embed it here. And then now you see that for this fragment, B, its FB is only here. You cannot embed outside. While for this fragment, it still has two choices, either here or here. So in that case, we always choose this first, and then we choose this. And then now this has only one choice of putting outside, so you put outside. So this is the right order. But before, our case was that you embed this. And this is the wrong order, because after embedding this, you must have consider this one, which has one choice, but this has two choices. So, you wait to embed this until you actually choose to wait here, this one. So that's what this theorem shows. And with this algorithm, actually it can run in quadratic time. So some constant times n square time. Because at first you just count the number of edges. If it's more than 3n minus 6 edges, it contradicts to the Euler's formula. So it is automatically non-planar. So there are at most 3n minus 6 edges. And in each iteration, you have to maintaining the list of the face boundary. There are at most linearly many faces. So you have to find them in linear many steps. So in each iteration, what you have to compute is linearly many things, and then the number of iterations is at most linearly many in n. So in total, the algorithm runs in quadratic time.